This is FP2 from 2024. Let's just do it. So Fermat's little theorem, or one version of it, says that as long as this number is prime, then this number to the power 1 less than this, so 21 to the power 22, is 1 mod 23. So that's quite useful because we can break 21 to the power 80 up a bunch of times into a bunch of 22s, all of which are just 1 mod 23, so they're kind of irrelevant. And then you've got left over 21 to the 14. Now, it's not immediately obvious what to do with this 21 to the 14. Obviously, you don't want to calculate it. Fermat's little theorem is now actually not very helpful anymore. You've already used it. So what do you do? Well, you notice that 21 is the same as minus 2 mod 23. And actually, dealing with powers of 2 isn't that bad, because I can maybe break these up. What I chose to do was say 2 to the power 5. The negative now, of course, doesn't matter because it's the power 14, which is even. But 2 to the power 5 is 32, which is 9 mod 23. So if you break it up into 2 to the 5, 2 to the 5, 2 to the 4, this is just 9 times 9, and this is 16. 9 times 9 is 81. You can then work out what 81 is, mod 23. It's what, 12, I guess that means. Then 12 times 16 is 192. You can work out what that is, mod 23, and it's 8. And that would be your answer to question 1, or at least one way of getting the answer. Rearrange this to make essentially a quadratic. This is going to feel very similar to doing differential equations. We just solve this. It's a repeated root, which means the solution is of the form an plus b times the roots to the power n. We just need this n in here because the root is repeated. So that's the first bit done. And now actually there's no other bit because there's essentially a 0 here. So now we can just shove in n is 1, gives us 4 over here, and n is 1 there, and n is 2 gives us 6 over there. We can tidy those up, and then you can just solve those very easily. And you get your answer just written down there like so. It will be done and dusted. Euclidean algorithm means that we take this number and take away copies of this number until we get as close to 0 as possible, being positive. And then likewise, you take this number, take away copies of that number until you get as close to 0 as possible, and then this number and this number, and then this number and this number. Once you get to 0, the remainder that you had before is the highest common factor. So in this case, the highest common factor is 6, and we'll put that down. Hence determine this. So this is just when we go backwards from here. So we start with this line here, and then we say, well, 12 is just this line here. So let's put this line in here in for 12, and then just arrange that in terms of, well, it's what? 1 copy plus 6 copies of 42 is 7 of them, minus 3 copies of 96. And then you take this line here for 42, and you put that object into here to give you this. So that's 7 copies of 234, minus 14, minus 17 copies of 96. And of course, check in the calculator that's right, but otherwise you'll have your 2 answers. Now solve this congruency equation here. Now 96 and 234 have a highest common factor of 6. Now crucially, 36 is also divisible by 6. So I'm allowed to divide all 3 of those numbers by 6 to make this here. Now I've left this on the screen. We found it just earlier here because it's going to be useful, because if I divide all 3 of these terms by 6, I make this. Just kind of similar to what I was doing there. And now if I maybe take away the 39s from both sides, we get this. But now if we make this mod 39, which is of course now the mod that we're working in, this just goes away because it is a multiple of 39, so it makes 1. And what I'm saying here is therefore minus 17 is the multiplicative inverse of 16 mod 39. So if I front multiply these things by minus 17, we'll just end up with 1x equals, and then this times minus 17 is that, and then just add copies of 39 on until you get a nice positive number, and then we'll have the congruence equation solved. Question 4 then. So given this is an eigenvector, so eigenvectors mean a times the vector is equal to some constant lambda times the vector, where the vector is the eigenvector and the value here is the eigenvalue. So find the eigenvalue. So we're just going to have to work out what a times v is. By multiplying this together, it makes this. Now this is clearly 3 times the original vector, because 2 times 3 is 6. So the eigenvalue is going to be 3. And then, of course, minus 1 times 3 would give you minus 3. So p is minus 1 times 3 gives you minus 3. So therefore, p has to be positive 3 to make this whole thing, I guess, minus 3. Yeah, that's cool. So now determine the remaining eigenvalues of A. So the eigenvalues, of course, are the determinant when you take away lambda from the leading diagonal and you set that determinant equal to 0. So we've got this into this determinant minus this into these 4's determinant, and then plus this, and then you don't care because 0 times anything is still 0. So you can expand this out very carefully, keep expanding. Usually in these questions, the reason that they give you one eigenvector or one eigenvalue is to help you solve the cubic that you get, but because this cubic just has a solution of 0, it's super easy to solve anyway. So it kind of is irrelevant. But the other eigenvalues are 0 and 6. So once we have the eigenvalues of 0 and 6, we can then find the eigenvectors. Now it's tempting to say if this value is 0, then v just has to be 0, but that's absolutely not true. In vectors and matrices world, you can totally get things to multiply together to make 0, even if neither of them are 0, which is quite cool in itself. But anyway, when you multiply this, you end up with this. So now we need to just find 4a plus 2b equals 0, and then this equals 0, and then this equals 0. All I really need to think about is that a has to equal minus 2b, right? Like if that thing is 0, just take the 2b over and divide by 2, you get this. If that thing has to be 0, then b has to equal c. And now we can just choose a to be like 1, and therefore b has to be minus 2. And therefore c has to be minus 2, and that will be an acceptable eigenvector. You can have any multiple of this as well. It's just an acceptable eigenvector. Likewise, for lambda equals 6, you need the matrix times by some ABC to equal 6 lots of ABC. And so then we figure that out. We set this equal to this, and rearrange gives you a has to equal b. I think as you take away 4a, you get 2a equals 2b, and then short a equals b. And then likewise for these two, you can rearrange to get this. So just set a equal to 2, maybe b equals 2, and that way c ends up being a nice whole number, which is nice. So that will be an acceptable eigenvector as well. So that's what we've got so far. And then it says determine blah, blah, blah. Hence determine a matrix P for which this happens. Now this is interesting because this looks a lot like what you're usually asked to do. But you're usually asked to do D equals P inverse A P. Not this. It looks a lot like it, but it's not quite. And it kind of makes a difference. The diagonal matrix D is still just the matrix with leading diagonals being the eigenvalues of the thing. So the eigenvalues are 3, 6, 0. So you can just write it like this. It doesn't matter which order you put those three in. Likewise, P is just the matrix that corresponds to, that has its columns are just the eigenvalues that correspond, sorry, the eigenvectors that corresponds to each of these eigenvalues. So the first column of P needs to be the eigenvector for 3. That's 2 minus 1, 2. The second column in my case needs to be when the eigenvalue is 0, and the third column needs to be when the eigenvalue is 6. If you did these as 3, 6, 0, then you just swap those two vectors around. However, this is a little bit unusual because this doesn't actually work, and you can try it if you like. If you do P transpose, which is just when you make the first row, the first column, and so on, and if you try and multiply these out, multiply out the first two if you like, then multiply out the second two, you can use the calculator to help you. You get this, which is not A, right? This is actually, but it is very closely related to A. It's actually just 9A. So actually, we can't really use this P. What we need to do is we need to use a third of P, because then when you use a third of P for the P and a third of P for the P transposed, a third times a third makes a ninth, and you'd cancel all this down to make A. So you actually just need to use a third of P for that. I could only find one question in the textbook that looked anything like that, but kind of a nice little trick. Worth bearing in mind in case it ever comes up, just to check this, and then you can find the right scaling down factor to make it work. Interesting. Anyway, a circle C in the complex plane is given by this. So this is when we just replace Z with X plus IY, and we do the fun little maths where we isolate the complex and the real parts for each. We use this rule here to get rid of the complex parts entirely, which is great. We square both sides, and then we collect everything together and rearrange, and we eventually end up with a beautiful little circle. And all the maths is pretty boring, but it ends up being just that. So this is a circle that is centered at 0, minus 1, radius 2. So it looks a bit like this. This is a bad drawing, but it looks a bit like it. And now we want to now color the area where this is bigger than this, not equal to. So this locus represents equal to. How do we find bigger than? Well, this is the point 3i, which is up there, and this is just at 0. So basically what this is saying is we want any points where the distance to this is twice the distance to that. So for example, here is okay, because apparently this distance is twice this distance. And likewise, here is okay, because apparently this distance is twice that distance, which looks kind of reasonable. So if we want the distance to 3i to be more than twice the distance to z, we want to be inside the circle. Just test that in your head. Just pick a value like this one here. The distance to 3i is definitely more than twice the distance to z if you're on z, right? So we want to be inside the circle, and we'll shade that. Now this transformation here, well, if you cube a complex number, right, you just triple the argument, and you cube the radius, or the modulus. So some words to that effect is all they were looking for there. It's just triple the argument, cube the modulus, something like that. Anyway, this region is given by this. Let's draw this first. That's just a line coming out at 0 along the initial line, and 1 at pi over 4, so it looks a bit like this. So we're inside this region. And if we're transforming it with 2, well, we just said that we triple the argument. The argument is pi over 4 here, so we triple that to be 3 pi over 4, which is over here somewhere. And of course, triple of 0 is 0, so anything in this region will become anything in this region. and then we cube the modulus, but that doesn't matter, right? Because let's say you were here, cubing the modulus just gets you further away on that line. And like, let's say you were here, you can't actually be here, by the way, because of this, but it's fine. And let's say you were here, you just triple or cube, sorry, the modulus, and you get further away. It doesn't matter. You just be further away in this space somewhere. So you can just be anywhere in this picture, and maybe just say that that argument there is 3 pi over 4, and you'll be done. Anyway, question 6, we finally get to do some integrating, which is, let's face it, what we were all waiting for. This one's really cool because usually you do reduction formulas when you, usually when you do reduction formulas, you do some integration by parts. For this one, not so much. For this one, you just start by thinking about in plus 2. And you don't do parts on this, you break this cos up into cos minus sine. So it's cos of nx, cos of 2x, minus cos of nx, minus sine of nx, sine of 2x. So I'm just using the compound angle formula here, where this angle is essentially nx plus 2x. So there's the two angles in here. And now, again, not too easy to think what to do here, but there's no cos of 2x here that we're aiming for. Keep your eye on what we're aiming for. There's none of that. So let's replace this cos 2x with cos squared minus sine squared, and sine 2x with 2 sine x cos x. And now this seems hopeful because if you look at this section over here, the sines will cancel out nicely. Now that's not enough on its own to make anything good, but we do need to get rid of the sine somehow. So let's, and notice how this in disguise, that's the integral of cos nx over sine x. So actually the sine x staying underneath this guy over here is actually fine, because that gives you the integral of in. Always keeping your eye on the prize, trying to find where you're going. Now these cos squared and sine squared doesn't seem too helpful, but if it was just sine squared, I could divide that by sine pretty easily. So what I'm going to do is I'm going to replace this cos squared with 1 minus sine squared, because then if I expand this out, this term, the cos nx times 1 over sine x, that's just in, right? I'm sort of looking forward to the point where I can break this fraction up into multiple different pieces, which is what I'm going to do here, right? So break it up here, and you can divide this sine easily. You can divide this sine because it just cancels. And, you know, this is the in that I'm looking for. So I'm not entirely sure what's going on here, but I've at least got the in. So that was kind of what I was going for. So that gets replaced with in. And then the rest of it, I'll just write like this. I'll factorize out the 2, put it under 1 integral so I can put a plus here. Hopefully that makes sense. So that's in, move the integral sign over here, but then it's minus both things, so you can just say it's minus into a plus, and then factorize out the 2 from both these terms, and you end up with this here. Now, how do we get this here? I've got the 2, fantastic. It's a minus, right, it should be, it's currently a minus, I don't really want it to be. But okay, how do we get this looking like this? Well, I want an n plus 1x. And this is quite a hard spot, but if you've done enough maths questions, you'll be able to see it. This is cos sine plus sine cos. Well, that looks a lot like sine of one thing plus another thing. So it is that sine of n plus 1x, right? Like if you were to break this up, this is sine nx plus x. So if you break this up, it becomes sine nx cos x plus cos nx sine x. That's how the sine one works. So it ends up being this. And then when we integrate this, of course, sine integrates to minus cos, so that gets rid of the minus here, so that's fantastic. Divide by n plus 1, of course, and you end up with exactly what they wanted you to get, which is really nice little question there. Okay, determine the value of this. Well, clearly we're just using n is 5 here. So, well, I5, based on what we just found, is I3 into 2 lots of cos 4x over 4. But I3, of course, we can use the rule again. I3 is just, well, I mean, it's just I1, I guess, plus 2 lots of cos 2x, I guess, over 2, because I has to be 1 to make I3. So that becomes that. Fine. And then I1, now I can't, looks like I can use the rule for n equals 1, but that would give me, if I wanted this to be an I1, that would give me this to be an I minus 1. I don't want to mess around with that. I can just evaluate I1, I think, because I1 is cos x over sine x, the integral of, which I think is just log cos. Sorry, log sine, because sine differentiates to cos. So I think that's just log sine. And you'll notice that I completely avoided these limits here, and that's because I'm just going to put them at the end, like this. So let's put the limits in. You can type this into a calculator. I tested myself and did this all by hand, but just type it into a calculator if you want to. These logs, you can divide the inputs because they're taking away. And when you do that, you end up with this. And now you just need to try and make it look like this. So you could write this, I guess, as 6 over 4 or to the power half, and that's 3 over 2. You bring the half to the front, and you end up with that there, which I think is the answer. Question 7 is the group theory question. So show that B is an element order 3. So that means that B cubed would be the identity. So let's just calculate that. So B squared first, just itself times itself. You get this, times that by another B. Oh, of course, this is, I should say, this is all evaluated mod 2. So when you do this, you get 1 times 1 plus 1 times 1 is 2. And then, of course, 1 times 1 plus 1 times 0 is 1, and the rest of it works out okay. But 2 is just 0 mod 2, right? So that becomes a 0. So every time we get to a 2, we're just going to write a 0. Now, if we do that times another copy of B, then we end up with, I think, just what we were looking for straight away, which is good. I don't know if there is, so it's 1. Yeah, no, it doesn't look like. Oh, that last term, 1 times 1, 1 times 1. Yeah, so that is also a 2, but it goes down to a 1. So it goes to a 0 because of the whole mod 2 thing. Anyway, that shows that B is an order element, is an element of order 3. Good. Determine the orders of the others. Well, I is clearly 1 because, yeah, it's already there. A, just multiply it by itself. It ends up being this straight away, so it's order 2. B we already did. C you can try, but it's order 2. You just have to do them all. It's fine. Doesn't take too long. And E ends up being another one that's order 3, just like B was. Good. So that's all that. Explain why G is not isomorphic to a cyclic group order 6. Now, a cyclic group means that one of the elements generates all of the others. So like this times itself would make B, and then times itself would make C, and then times itself again would make D, and then again would make E. But that means its order itself would be 6 because it just cycles through all the other ones. Now, we don't have an element order 6, so therefore they can't be isomorphic because the orders wouldn't match up. There's nothing over the order 6 to match the order 6 that is definitely in the cyclic group. The group of symmetries of a regular hexagon. Now, if we think about moving a hexagon around maybe, now the identity just says don't do anything. Now, this one had order 2, so we could also almost imagine A just being a reflection like this. You reflect it over, this corner goes here, this one goes here, this one goes here, and then if you reflect it back again, you get back to where you started, so that would work. B was order 3, so let's think on our heads here. What order 3 could you do with this hexagon? Well, you could move it around 2 spots, right? Like this could go there, and this could go there, and so on. If you did that 3 times, it would get back to where it started. So B could represent that. C was order 2. You could reflect it like this, you could reflect it like this again, or you could rotate it kind of 3 ways across. So this goes all the way over there, this goes all over there, and so on. And that would also be order 2. But then you think, okay, well, why is this not isomorphic then? Well, a regular hexagon, you could just rotate one way, one along, right? You could just put this here, and 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 this here. And likewise, you could go backwards, this here, this here, this here, and so on. So there should be at least 2 elements, order 6. And we don't have any still, so they can't be isomorphic either. Now we need an isomorphism, so I've set the table up ready from G to H. You draw the elements in G, going to all the ones in H. Now this is kind of you have to be a bit careful. What I like to do when I do these is just set out all the things that I know about all the elements. So obviously we have one element of order 1, that's the I. This is about G. We had 3 elements order 2. We had 2 elements order 3. Also notice that B and 3 are inverses of each other. Because if you just swap those over and make those negative, -1 is the same as 1 modulo 2. So B just becomes E, so B and E are inverses. So that's kind of the obvious stuff out the way. So maybe E was rotating it anti-clockwise as opposed to clockwise, and that would make B and E inverses, of course. Now, what about these ones over here? Well, clearly E is the order 1 because it's not doing anything. A, that's order 3, it looks like, because 1 goes to 2, which goes to 3, which goes back to 1. So you'd have to apply this 3 times to get 1 back to itself. And likewise, B is also that. And then the order 2s are just along this row here, because you just swap these 2 and then you swap them back again, and 1 isn't changing. So those are all order 2s. So, okay, it's tempting to just say, well, I has to be the same as E. And then any of A, C, and D can be any of C, D, and F. And then A and B just have to be any of B and E. And that's not quite right. You have to be a bit more careful than that. Obviously, I does have to be E. Now, you can choose which one B and E are. I just chose B to be A and E to be B. Now, once you've made that choice, you do have to be a bit careful here because there's slightly more going on here than just the orders and these 2 inverses. For example, if I take AB, so if I apply B first and then do A, because that's how matrices work, right? So if I apply B first and then do A, but essentially just multiply A and B together, I end up with this. And notice that that's also in the group, that's D. So what happens if I take what I think the equivalents of A and B are in this thing here? So I've said B is the equivalent of little a. So what happens if I take little a, and let's just say we transpose that with C. Let's just go with C. So A sends 1 to 2, and then I would send 1 to 1. Sorry, A sends 1 to 2, and then I would send 2 to 3. So in this composition, 1 would get sent to 3. And you do this the other way around. You do A first, then C, whereas here it was B first, then A, but it doesn't. It only matters for the very end. So A, then C. So A, 1 goes to 2, 2 goes to 3, so 1 goes to 3. Likewise, 2 goes to 3, which goes to 2, so 2 goes to 2, and 3 goes to 1, which goes to 1, so it goes to 1. And now that, if we notice, is the same as F. So if I'm saying that B is A, because again, here B comes first, then A, so A comes first, then C. So if B is A, then that means big A would have to be little c, which forces D to be F. And then, of course, C would have to be the last one left over, which is D. But you can't just write. It's really tempting to say these could just swap over, but they can't because the elements themselves are interacting in this other way as well. So it has to be, well, there are a bunch of orders you can make, but this is one of them. Again, you could have swapped B and E at the start, and then it would have been made a different as well, but this would be one acceptable way of doing it. And lastly, we have the integration question, or another of the integration questions, I guess. Firstly, we're shown this curve here, show that this thing here. So, okay, well, this seems fairly straightforward. dy by dx, we can start with, we can look up the formula, of course, because who's going to memorize that? Dy by dx is just a ninth times 9 over 2, which is a half into this. And we can square that because it's going to need to be squared when it goes in. A half squared is a quarter. This squared is just this to the power 2, and then you times these indices to make 2/9 of x. And then, of course, you can put that in. Y is just as described there, and that's all fine. We're integrating between 0 and 9, so that's all fine too. We can bring out the 9 halves to just make a 9 on the outside. We can factorize out a quarter from this guy, but only if you then apply power of a half later. A quarter to the power half is a half, and then you can take the half out. And that's how we end up with 9 over 2 pi at the front. So k is 9 over 2 pi, and the rest of it is absolutely fine. Use the substitution this to show this thing here. Now, this is pretty wild. So du equals a ninth e to the power 9th dx, clearly. We also, I guess, we could times that by this, and this itself is just 1 over u. So it ends up being this. So that's the thing that I'm getting ready to throw that in there. This is obviously just u itself. And now this is, I think, u squared, as we've seen before. Because if we just square both sides here, we end up with e to the 2/9 of x. Now over here, I'm doing the limits. So if I put in x is 9, 9th times 9 is just 1, so this becomes e, and if you put in x is 0, you get e to the 0, which is 1. So, and then, like I said, when you square, you get this. So I think this all turns out to this. And I got really confused here, because the u's obviously cancel. You bring the 9 out to the front. Great, I'm seeing the 9, a and b are clearly e and 1, that's fine. And I end up with this. And now the reason I was confused about this is because I know how to do this integral. You use a trig substitution, obviously. Like, why would you do anything else? So I was really confused as to what on earth was going on here? How am I supposed to get to this? Well, it's because they're attempting to talk you through a really interesting way of doing this integral. Because notice that actually this integrates really nicely, because this here is just the derivative of this down here with a factor of 4 missing. So this is just reverse chain rule, right? If you just had this to the power of a half, you bring the half down, you derive this thing, it gives you this, and then the power of a quarter at the front helps make the coefficients right. And this is just from the formula book, of course. So they're saying, don't do a trig substitution. Make this look like this, and then you could just integrate it. So how do we do that? Well, we're going to times swap and bump by the same root, which gives us, of course, just 4 plus u squared over that entire root. We're now going to try and make this object. So what I'm going to do is I'm going to say this is the same as 2 plus u squared plus 2, and then break the fraction down here to make this. Because now 2 times 9 makes 18, and then I'll have 1 over 4 plus u squared on the outside. So that's perfect. So that looks absolutely fantastic. And now the rest of it is actually pretty straightforward, because all I have to do is times the first bit by u over u to make the numerator match. It's a pretty obvious step, just need to make those match. And then, of course, this times this you can't do unless you write this as root u squared, and now you can put the thing inside, and you end up with exactly what they wanted you to get. And likewise, like I said before, this works really well because both of those things are perfectly integrable. Now, the small trick you have to notice here is that they've dropped the k from all of this garbage. So we have to put the k back in for them. So I times both of these by 9 over 2 pi. So I put that in there for them. And now, like I said, we can just integrate these, right? Like this integrates this, because if you were to differentiate this, the half comes down to make a quarter. This becomes this, the minus half, which is this root here. The derivative, this is 8u plus 4u cubed. You can cancel that down with the quarter, to make 2u plus u cubed. And so it's all perfect. And likewise, this you look up in the form book is arcshine. It's actually rshine, but PowerPoint doesn't understand maths, so it calls it arcshine, but it doesn't really matter. You can just type this into the calculator, of course, and you end up with this as your final answer. Thank you so much for watching, and I'll see you next time.